So in this question, we're trying to find different iterated integral for the triple integral over the solid that is given right there. And so the solid has basically here we see z equal to y on one side, and then you can tell that there is the y equal to x squared, which is a cylinder, a parabolic cylinder, is on the other side that I can't see. You see the arrow goes behind the solid. And on this side of the solid, x equal to 1. So let's try to set this up as a z simple solid. See, z equal to y is the upper surface. If I go in terms of y, and I could have drawn an arrow, z equal to 0 on the bottom and z equal to y on top. So the inner integral is f of x and y dz from 0 to y. Now, what is remaining if we do the z simple is the projection onto xy plane. So the projection onto xy plane, and I can tell, see, that's this line. This line is going to be, so that one right there, and this one right here. And what you see in the dashed part is actually the intersection of the y equal to x squared and z equal to 0, which is going to be just y equal to x squared. So y equal to x squared here, here x equal to 1, here y equal to 0. And so I can set this up either as vertically or horizontally simple region. And so again, this one is x, this one is y, because z is already used. And let's set it up as vertically simple. And so that would be dy and then dx. dy, y goes from 0 to x squared, and x goes from 0 to 1. Now, if I want to change the outer ones, that the double integral part, inner integral, see, in all of these situations, the inner integral basically becomes the integrand of the double integral of the outer integrals, or outer and middle integral. So now if I want to change this order, I have to use this direction, and in that direction dx dy. In x direction, we start from square root of y, and we end at x equal to 1. Sorry, in the wrong place. That's the middle one. Square root of y right here is square root of y. And we end at 1. And for y, we go from 0 to 1. And so now these are z inside. Can we do, let's say, x inside? And so this time, can I have this as z simple? So let's see, z simple means, I'm sorry, x simple. X simple, I can draw an arrow from that, from this cylinder into x equal to 1. So the inner integral considered as x simple starts at the cylinder, solve for x, get square root of y, and 2x equal to 1 dx. Now, when it's x simple, we have to project everything into z. And when you're projecting everything into z, basically you have to look at projections of that triangle. And the triangle looks like this. This one is 1. It's y and z, and this is 1. And I have this shape. And so if I want to make it go direction of z, then it starts at z equal to 0 and it goes to z equal to y. And so that's the middle one is going to be just that. And then the outer one, y goes from 0 to 1. And switching this is not too difficult. Switching the double integral, that is the outside, is not that difficult. I can start again. The most inner doesn't change. Ooh, this is x and y dx. And so the switching with dy dz and dy dz, that's the direction with the direction of y, starts at y equal to z and ends at y equal to 1. And for z, it goes from 0 to 1. So what is left is just the y simple, make it into y simple region. And so let's do one of the y simple regions. Again, switching the two outer ones are not, or middle and outer integral is not that hard. So just maybe set up one in the as a y simple. And so y simple starts from this, actually this, and then it goes all the way to the cylinder. So y simple starts at the plane z equal to y, that's y equal to z, then it goes to y equal to x squared. Then if you look at basically what you want to do is to look at the projection of that into xz plane, and into xz plane it seems like the shape looks like this. I can see x and z, and I can see goes like that. And so that one, x equal to 1, z equal to 0, and I have to figure out what that is. And to figure out what that is, it's basically, I can see it's between these two equations. I can get rid of y, and I can get z equal to x squared. So the relationship between z and x on that right there, oops, sorry, there you go, right there, is just the relationship between z and x squared is going to be z equal to x squared, and that's what you see in the projection. And so right, and so I have, if I do z first and then x, I go from 0 to x squared, and x goes from 0 to 1. And again, switching these two is not that difficult as long as you know all of these. And so one thing to remember when you're doing all these blue integrals are the most inner, always considering a surface. But then as soon as I go to the red ones, I actually try to intersect and find a relationship for those boundaries, so I can put those boundaries. See, there's a boundary right here, um, right here, right here, and I'm sorry, the graph of the boundaries right there, right here, right there. And so that's when I do the intersection. So for most inner, all you're doing is finding the surfaces that the most inner variable goes from this surface to the other surface. That's all you're doing basically.